In this segment, we'll talk about what the relationship between the absolute, relative, or approximate error and the number of significant digits you find to be correct is. So, for example, you are in a numerical method going to be calculating absolute, relative, approximate errors, which is basically calculating your current approximation and subtracting it from your previous approximation divided by the current approximation, and assuming you are calculating it as a percentage, we multiply by 100. So when do we know that, hey, we need to no longer find the current approximations? Because for example, we are going to be finding the sum of a series. We will continue to add one term at a time, and those become our current approximations. But when do we know when we have to stop the current approximations? In this case, we may have something called a pre-specified tolerance. What that simply implies is that you have pre-decided that, hey, you want the absolute relative approximation to be less than some number, epsilon s, and that's when you want to stop the numerical method which you are using to calculate an approximate answer. So in that case, what we have basically is that when epsilon a is less than or equal to epsilon s, that is when you want to stop your numerical method, whether it is to find the sum of a series, whether it is to find root of an equation, whether it is to integrate a function, and so on and so forth. Now, sometimes what you'll find out is that the pre-specified tolerance might be given in terms of number of significant digits you want correct in your answer. Let's suppose somebody says, hey, I want 2 significant digits to be correct in my answer while you are conducting this numerical method. What does that mean? So there is a nice theorem which relates the number of significant digits which are at least correct to the absolute relative approximate error you are getting. What is that theorem? It says that if you want at least m significant digits to be correct in your answer, then you will need to have an absolute relative approximation which is less than this particular quantity, 0.5 times 10 to the power 2 minus m%. So for example, when we're saying, hey, we want 2 significant digits to be correct in my answer, what that simply is telling you is that you want absolute relative approximation to be less than or equal to 0.5 times 10 to the power 2 minus 2, which is equal to 0.5%. So this becomes your pre-specified tolerance. And it also relates that, hey, if your absolute relative approximation turns out to be less than 0.5%, then 2 significant digits are at least correct in your answer. So let's suppose if I want 1 significant digit to be correct in my answer, then my absolute relative approximation needs to be less than 0.5 times 10 to the power 2 minus m, which is 5%. So one of the things which is important to note here is that if it goes both ways, that if somebody says, hey, you want 2 significant digits to be correct in your answer, then you will say, hey, the absolute relative approximation is less than 0.5%. However, if your absolute relative approximation turns out to be less than or equal to 0.5%, then you are guaranteed that there are at least 2 significant digits to be at least correct in your answer. So you should be able to go both ways and interpret it correctly so far as this theorem is concerned. And that's the end of this segment.